Okay, hold on. Let's make sure that. Okay. Okay. So don't worry if you guys don't catch what I say, but it's because it's recorded, so I'll post it on my YouTube channel after that. And then yeah, so I want to try to keep it interactive. You guys are free to ask questions at any point in time. Don't be afraid to interrupt. So my goal in today's talk will be to give you some intuition for special relativity. I'm sure all of you have done the calculations and whatnot, but this is some intuition I developed after my physics Olympiad journey when studying math mainly. So I'll be mainly trying to motivate special relativity from purely mathematical perspective. And you can see that we actually get quite far. And the mathematical structures that we get is actually quite nice. Yeah. So once again, please ask any questions at point in time. Okay, so we're going to start off from something called the space-time interval. The fundamental axiom of special relativity says that if I have two events, right, the space-time interval separating the two events is invariant under all inertial reference frames. So what is an event? An event could be an explosion at some point in time and space. It could be existence of something. For example, the ball is at this location at this point in time. Or it could be even a measurement of a field value at a point in time and space. For example, electric field, right? So this is everything that we're going to start from. And we'll see that everything actually arises from this, right, mathematically. So we see that space-time interval is something like it is a separation in the spatial squared and the time separation as a squared, but the time separation has a minus sign in front of it. So the exponential part over here you're familiar with, right? It's just the Euclidean distance, but the time part has a minus sign. And it turns out that this minus sign is going to be responsible for all the time dilation, every single thing we see. So yeah, any questions point in time? No? Okay. So first of all, we'd like to check what coordinate transformations, right, leave this space-time interval invariant. Yeah. So okay, I was gonna get you guys to guess, but I guess it's here already. So surprisingly, right, there's actually a lot of mathematical transformations that leave this invariant. Not all of them are physical. For example, if I take the time coordinate of the two events and I flip it around, right, then you see that the delta t picks up a minus sign. But when I square it, the minus sign is gone. So actually time reversal leaves the space-time interval invariant, right? As well as parity. If I take the space-time events and I mirror it about the x-axis or the y-axis or the z-axis, right, it actually leaves the space-time interval invariant as well. So this is purely looking at the math of the space-time interval. Okay. So these are discrete transformations on the space-time coordinates, right? Discrete in that you can either do it or you can don't do it, right? There's also continuous symmetries of this space-time interval. If I take the two events, right, their time coordinates, and I move it by some fixed amount in time, right, it corresponds to starting the clock later, right? And that leaves delta t invariant, right? Delta t is the difference between the two, the a cancels out. Likewise, space translations. And here comes the interesting part where you actually have rotations of sorts. So for Euclidean distance, don't worry if you don't understand SO3, right? It's a Lie group and stuff. That's more theoretical physics. But you can actually, what that means, we have spatial rotations that leave the Euclidean part invariant. So the x squared plus y squared plus z squared is invariant under rotations, right? That corresponds to, you have a stick, right? You have a stick like this pen. You rotate the pen, right? The length remains unchanged, correct? Right? Okay, so if we express it in terms of Euler angles, rotation can be parameterized by three angles, Euler angles, right? Theta, phi, and psi, right? And we can rotate it by any Euler angles, any three Euler angles. Yeah, so this is a general form of rotation that leaves the Euclidean part, the spatial part, x squared plus y squared invariant. Okay, so far? And this rotation, spatial rotation doesn't touch the time. Okay, so far? Okay. But what is more interesting is that we can actually bring in the rotation, but of the time component. So now we're saying actually we can not only rotate the three spatial components, can not only rotate this pen in three spatial directions, but I can actually bring in the time and rotate it along with the space as well. So that's what they mean by treating space and time as equal footing, right? You don't really care that they are different physically, you just mathematically rotate them as if they are the same thing. And turns out because of the minus sign over here, right? It's not going to be spatial rotations. It's going to be hyperbolic rotations. So I'll elaborate much more on this later. But roughly speaking, see the cosine and sine over here. That just correspond to replacing the cosine and sine with cosine and sinh, right? So yeah, I'll elaborate more on that. Okay, so first of all these math, right? What does it have to do anything to do with physics? We can interpret them in physics. So interpretation of math in physics, time reversal, parity, all these, right? I would like to draw your attention to perhaps spatial translations, which just corresponds to, right, being the two observers being at different locations when they measure the space-time interval of the two events. And I also like to draw attention to Lorentz boost. So it turns out that hyperbolic space-time rotations actually corresponds to different velocities. I have a nice Desmos graph to show that later. And so we're gonna spend the rest of the talking about how Lorentz boost gives rise to different velocities. So yeah, everyone good so far? Okay, so first of all, spatial rotations. This is a general 3D rotation, right? I'd just like to focus on 2D rotation matrix, right? So just restricting myself to rotating about the XY plane for now, because it's easier to draw the parallels in math. So if this is a rotation matrix, if I have a point in space, in 2D space, with coordinates x and y, I arrange it like a vector like that. I apply the matrix to it. This is just a linear transformation on that point, right? And it gives me a new x coordinate, a new y coordinate. If the length of the length in 2D space is x squared plus y squared, we can check that if we take the new x coordinate squared and the new y coordinate squared, if we work out the trigo, you can see that some terms cancel out. Cosine squared plus sine squared is 1. So you actually get back the original length. In other words, 2D rotation, this 2D rotation matrix leaves the 2D length, Euclidean length invariant. Okay? So now the question is, how does this generalize to hyperbolic rotations? So we just replace the normal trigo with hyperbolic trigo. So what if our length was defined as x squared minus y squared instead of x squared plus y squared, right? Okay, so I'd like to talk a bit more about this. X squared minus y squared is the length, but does it mean that length can be negative if y is bigger than x? Yes, indeed. The length, in this new definition of length, it can be negative. That seems unintuitive, but mathematically speaking, is a valid length. Yeah. So this is don't think of the length as a physical length. Think of it as just a quantity, right? Just a quantity that I measure between 2 points. Okay. So what leaves the x squared minus y squared invariant? It turns out it's a hyperbolic trigo. If I apply this matrix to xy, new x coordinate, new x coordinate, square it, new x squared minus new y squared, I get back the original one. And this is owing to, previously we had cosine squared plus sine squared equals to 1. Now we have cosine squared minus sine squared equals to 1. Okay? Wait, how do I pronounce? Sine. Can we agree that it's sine?
No, shine.
Shine. That doesn't make sense, but okay, but Kosh, we can all agree on Kosh, right? Shine. Okay. But Kosh is Kosh, right? Kosh. Not Chosh or something. Huh? Yeah, question. Sorry? 914. Oh yeah. Apologies. This is typo over here. This will be shine squared. Yeah. Okay. And how do I pronounce tench?
No one knows.
Okay, I'll say okay. Okay. So anyway, enough with math, right? Let's do some visualizations. Okay, so I have this Desmos thing over here. The link in the slide is actually outdated, so I'll update the thing later. Okay, so give me a while I set it up. So I'm going to first draw a circle, right? This is a circle of constant radius. Everyone can see? Yeah. Okay. Yeah, wait, 3 points. So let's first talk about rotations. Everyone is familiar with rotations. So the black dots are being rotated by two-dimensional rotations, right? Parametrized by angle. Yeah. So nothing much here. So where do the black dots move along? They move along points of constant radius, right? Constant distance from the origin, right? So the circles over here are constant distance. So what are the constant distance? What are the lines of constant distance, the loci of constant distance for a hyperbolic metric, right? For x squared minus y squared, it corresponds to hyperbolas, right? Hence the name. So what would hyperbolic rotations correspond to? It just corresponds to moving points along the hyperbola, right? These are actually Lorentz transformations. So yeah, so moving points along the hyperbola, and they are parameterized by a hyperbolic angle, which turns out to be rapidity later, which roughly gives you the speed. Okay, so that's that. Okay, so hyperbolic rotations, how can we interpret them? If the x-axis, if the vertical axis in this case is time, and the horizontal axis in this case is space, then this actually hyperbolic rotations actually correspond to transformations between frames of different velocity. So why is that so? It's because if I pause it over here, right, you see the green dots over here, they are moving at a constant rate, constant slope, right, with respect to time. So the x-coordinate, initially it's at 0, 0. After some time, the x-coordinate has shifted by some amount. The next time interval, another constant amount, and basically velocity, right, moving at your position is changing with respect to time. Yeah. So okay, so how do we make this connection with velocity precise? We consider Lorentz transforming the 0, 1 point. So if I consider, okay, consider Lorentz transforming the 1, 0 point. It turns out to be this. And so this new vector is the location of this dot over here. So then I can find the gradient of this dot. So if I consider different hyperbolic angles, right, this corresponds to a transformation to a frame where it's low velocity, right? It's not very slanted. But if I bring it to the extreme, right, this corresponds to a frame with higher velocity. So how do we relate the hyperbolic angle with the velocity? If I apply it to this 1, 0, this turns out that the inverse slope of the graph, the inverse slope of this green dots is precisely the velocity. If I calculate the inverse slope using the coordinates, turns out that the hyperbolic angle that I rotated by is if I take the tanh of it, right, I'll get the velocity. And this velocity is divided by c. We often use beta instead of we often use beta basically it's interchangeable with v. You set c to equals to 1 like in most texts, then beta is equals to v precisely. So whenever you see beta, just think velocity. Okay. So this w is known as rapidity, which you might see in some of your notes. So I hope that this connection is clearer. Okay, so great. So now we know that hyperbolic rotations in space-time correspond to boost to different Lorentz, different inertial frames with different velocities. Now if I have a rotation, right? If I have a rotation and I rotate a point by an angle theta 1 and theta 2, right? So I do 2 rotations on it, the angles add, right? And what if I do it for hyperbolic trigo? Turns out the rapidity is add. So we can work out the composition of 2 transformations is just the multiplication of the matrices because of linear algebra. And if I apply hyperbolic trigo angles, I get that the 2 Lorentz boosts, one with rapidity u, one with w, gives me a single Lorentz boost with rapidity w plus u, right? And we see that means that if I boost to a frame with velocity v1, and then from that frame I boost to velocity with v2, that does not correspond to boosting with one boost of v1 plus v2. Instead, the rapidities add together, not the velocities. So very nicely, I see that if I want to find out how the velocities add, right, I just use the hyperbolic tanh formula, and we see that we just recovered velocity addition in at least in one direction. Make sense? So purely from mathematical workings, right? We see that we derive velocity addition. So that's great. Now I said that this matrix is a Lorentz boost, but maybe some of you might be more familiar with this type of Lorentz boost, right? So actually the connection is just given by these formulas over here. So yeah. Okay, so yeah, so this is just a connection. Okay, Okay, so this is in the full 4 dimensions. I leave the X, Y, and Z. I don't touch it. Right? I just boost in the X direction. Okay. So time dilation. How do you understand time dilation? Okay, I have a nice Desmos graph again. Okay, so Lorentz boost. Okay, so this blue line is the new frame. Sorry, let me just try to find the things that I want to find. Okay. Okay, yeah, okay, so I hope you can see it, but the blue line is the frame of the moving observer. The blue line is the blue line is the world world line of the moving observer. And if I go to a frame where he is stationary, you see that the orange lines correspond to from his perspective what his equal times, right? But if I Lorentz boost to a frame where he is moving, then his notion of equal times in the moving frame will be stretched out, right? So this is what we see. We see the distance between as we Lorentz boost further and further, right? The distance between the orange lines increase. That corresponds to time dilation. I can just show the twins paradox. Let me try to find the right graphs to bring up. I had a line through this, but I can't find it. Okay, not really. Okay, I guess this would do. Yeah, okay, so if I Lorentz boost, let's say I have two observers, red and blue, right? So we're going through different frames. In the frame that blue is stationary, he will see that red's time is slow, right? He'll see that the red's dots, when projected onto the vertical axis, is slower than him. But when I boost to a frame where the red is stationary, then we see that blue, we will see that red will see that blue is the one who is slow. In other words, if two twins separate apart, right? Each twin A will see that twin B is moving slower, the time is moving slower. Twin B will see that twin A's time is moving slower. And that seems very unintuitive because we think of time as absolute. And our intuition is that time is some universal time. So who is really slower? The answer is both of them are correct from their own perspective. And so I have an analogy to draw with normal rotations, right? That makes this clearer. So if I just have two normal vectors, right, in Euclidean space, I do 2D rotations on it, right? If I rotate the blue vector such that this is normal 2D rotations, okay, not hyperbolic ones. If I run blue such that it's vertical, and I take the red one and project it down, the blue guy will think that red guy is shorter. If I go to the red frame, right, where red is vertical, and I project the blue down, the red guy will think that the blue is shorter. Who is really shorter? The answer is that there's no such thing, right? Both of them are equal length, just that you're rotating to different frames. And in some sense, the length of it in blue's perspective here, the length of red, the missing length of red has gone into another dimension, right? That's how we see it. Very intuitive in terms of normal rotations. Now, hyperbolic rotations, right, is the opposite, right? Instead of thinking the other guy is shorter, you think the other guy is longer. So in the blue's frame, he'll think that red time is slower. In red's frame, he'll think that blue's time is longer. Yeah. So that's basically it. It's around. Oh, I hope that helps. Yeah. Okay, so that's time dilation. How about length contraction? Length contraction, very similar. We consider in the blue frame, the stick is orange. It's an orange stick. Is moving. It's sweeping out some gold sheet, like that. And we Lorentz goes to another frame where the stick is moving. Then we get a cyan stick, the blue stick, right? Now you see that in the new frame, it seems like the blue stick is longer, but So shouldn't it be length dilation instead of length contraction? So that seems to be weird. But the answer is that no, it's actually length contraction, because how do we measure the length of something? We measure the length. I say the length of this red pen is defined by the difference in coordinates of the two ends at the same time, right? So the funny thing is that if I Lorentz boost, right, the orange stick to the blue stick, you see that the two ends, originally it was at the same time, but when I Lorentz boost, they are different times. So it's kind of like, if I say that the length here is longer, it's kind of saying like, okay, I'm going to throw this red stick, right? I'm going to measure the tail end, right, at the location of the tail end at this point in time. And after 10 seconds, right, I'm going to measure the length of the head, right? I'm going to take the difference. So if I throw this pen across and it drops on the floor, am I going to say that the length of this red pen is that point on the floor minus the tail? No, right? Because when I measure length, I must measure them at equal time slices, right? And the idea is that Lorentz transformations mixes up these equal time slices. Two things at equal time, no longer at equal time after that. So yeah, so if I do figure out the math, right, at equal time slice, the boosted frame will see that this orange stick has become the green stick, right? And if I work out the coordinates, I can find this one just by boosting this point, right? Just apply. Then this one I can find the gradient of the line by using rapidity, then project it down. I get this singe tangent, the shine tangent, right? And then I take the difference of the 2 points, I get the original length contraction factor that we see. So length contraction, you need to take note that we measure length at equal time slices. Right, so we've covered a few of the main hallmarks of special relativity. How about laws of simultaneity? Okay, so there's a very classic example for this. It is the train and the. Okay, so laws. So you have seen the experiment where you are in a train, right? Of this guy, he's in a train. He shines light towards the two ends, and then from another perspective, right, the light reaches the two ends at different timings. And if this guy is moving right, one A will be faster than B. The light will reach A faster than the light will reach B. If he's moving the other direction, the light will reach B faster than it reaches A. So whether two events, one comes first or another comes, whether A comes first or B comes first, it depends on your reference frame. So then that might seem very concerning, because if you have loss of simultaneity, then does that mean causality is lost? And it turns out, fortunately, not. So if A comes before B or B comes before A, depends on the reference frame. Does it mean that whether A causes B or B causes A also depends? So it'll be wild if it was a case that causality is frame dependent, because that would mean that if I press this button over here, the bomb explodes, right? In another frame, you see the bomb explode first, then I press the button. That doesn't seem to make sense. But thankfully, it's not lost. So the usual construction is a light cone. So if A and B are two events in space-time, how you can tell whether A can affect B or B can affect A is by drawing the light cone. So this is also another very common thing. So if okay, the internet's kind of slow, but it's okay. Okay, never mind, I'll just draw on the board. Tell me if it comes up. So if I have if I have A, right, and B, to tell whether A can affect B, right, I draw the light cone of A, which is 45-degree line if the vertical axis is CT and horizontal axis is X. So it turns out Lorentz transformations will only bring B, right, within this region of the light cone. So the upper region is called the time-like space, the separation. The horizontal over here is called the space-like region. So all Lorentz transformations will keep B within the space-like region, meaning that B can go here, B can go, rotations about B will bring it about. So Lorentz transformations will only bring B and keep it within here. And if I say that A cannot affect B in one frame, A cannot affect B in all frames. Right? But on the other hand, if let's say there's another event C over here, right? C can bring the Lorentz transformation will bring C within this light frame, this light cone, right? So yeah, so that leads us to the definition of causality. Okay, I don't think I need to. So definition of causality is depends on the space-time interval, right? If it's positive in this convention, then it's space-like and so on. I think you guys have probably seen this before. So there's also another corollary, which is that if two events are space-like separated, there'll be a frame where if two events A and B are space-like separated, there'll be a frame where A comes before B, and there'll also be another frame where B comes before A. In other words, they cannot affect each other. It makes sense that they cannot affect each other, right? And if the two events are like separated, then there exists a frame where A and B are the same spatial location, right? And hence, yeah. So that's just that. If two frames are like separated, then they'll always remain like separated in all space, in all frames of reference, all inertial frames. Okay, so that's roughly the kinematics of sorry, that was just some preliminary stuff. Let's talk about the kinematics. So what do we want when we talk about kinematics of stuff? We want to talk about paths of objects, right? Kinematics is how something travels through space, right? So it turns out paths they're just curves through space-time. So that corresponds to a function from the real numbers to whatever space-time you have, the target space. When I choose any parameterization we want, but it turns out the most natural parameterization is proper time. So in other words, right, the curve is parameterized by the proper time, which is the time that the object experiences if he was in a stationary frame. So this is just talking about parameterization of a curve. That's what people mean by proper time. It's just a parameterization of a curve. Yeah, so question, why don't we want to parameterize the curve by the time in that frame? Why don't, instead of using this weird tau here, why don't I want to use the t? Doesn't that seem more natural to use time as parameterization? Anyone wants to give a guess?
T changes based on T.
Yeah, correct. So the answer is that t under Lorentz transformations they change. So the reason why we want to use tau as a parameterization is because when you have a parameter, if you have a parameter describing a curve, you can take the derivative. You can take the derivative of the curve with respect to the parameter. So derivative of a curve with respect to a parameter will give you the vector. And that's what 4 vectors is about. So you take that's why we always take the derivative with respect to proper time, because the proper time is actually just a parameter of the curve. Right? If you think of the proper time as the time that the guy measures in his rest frame, then it doesn't really make sense when you say you take the derivative proper time, like what's going on. But if you take that definition, abstract it away to say that his proper time parameterizes the curve, then it totally makes sense why we do this, right? And why we do this is because under Lorentz transformations, the 4 vectors, the vectors just rotate using Lorentz transformations, right? When it moves to another frame, they just rotate using Lorentz transformation. If we use t over here, then if we Lorentz transform the t in the bottom, then it's going to lead to very non-linear transformations, and we don't enjoy the tools of linear algebra that much after that. So everything we do in 4 vectors, we differentiate with respect to proper time, because that gives you a 4 vector and not some weird thing that transforms non-linearly. So I'm sure that when you guys do dynamics questions, you always deal with the 4 momentum, right? You add it up, you do whatever, transform it. And this is a derivation of the velocity addition in general directions, right? When you do velocity addition in general directions, you just add up the 4 vectors basically. But if you didn't parameterize it with proper time, you cannot do this because basically you cannot use linear algebra anymore. So adding 4 vectors doesn't really make much sense. So the linear property over here that we obtain, the linear property that Lorentz transformation of 2 4 vectors when added up together is just the addition of each of the individual Lorentz 4 vectors transformed. So this linear property applies on 4 vectors, and the reason why it does is all thanks to the proper time. So without the proper time, if we didn't parameterize it this way, we don't get to use linear algebra in special relativity. Yeah. Okay, so now we can describe kinematics. How about dynamics? Right. So how something evolves in time depends on the action. Right. Usually we say, what's the Lagrangian? It's the kinetic energy minus the potential energy. But in this case, we don't have anything to work with yet. We haven't even defined energy, right? And potential energy. So what do we work with? That's how we can work with proper time. So action is actually the Lagrangian, the action is actually just the proper time, the integral of proper time. If we do this, so why do we want to do this? why can't we do other stuff? Why can't we do dt? It's because we want the action to be invariant under all Lorentz transformations, right? When you boost to a different frame, you don't want the action to change because they'll change the physics. So the statement that physics doesn't change in different reference frames, right? Physics invariant under all reference frames is a statement that action is invariant under all reference frames. So if we have this is basically the only sensible thing we can have. The MC squared is just for making sure the dimensions make sense. And if we go to a particular frame, right, we get this expression, right? And this one, if you take this expression and you Taylor expand, you get MC squared plus half MV squared. You recover Lorentz, you cover Newtonian mechanics. So that's convenient. That's nice, right? But instead of doing that, I'm gonna apply Euler-Lagrange equations. So Euler-Lagrange equations, what's the canonical momentum of a coordinate is the partial derivative with respect to the velocity. So that's the definition of momentum in Hamiltonian mechanics. Now Hamilton, I just apply it, I get derivative of this is 0. So this is how we obtain momentum. This is how we obtain relativistic momentum in special relativity. Yeah. Then okay, so now I have this 3 momentum, right? This relativistic momentum, but what about the time component? It turns out we can make this. It's because this is the d over d tau of the x coordinate, right? And if the x coordinate, of the x3 vector, it's very easy to say that why not I just I define the 0 component to be this over here, right? So the d over d tau of the time coordinate, and that turns out to be this. Now this, at the moment, I haven't said what this is yet. I just say, because I want the 4 velocity to be the derivative with respect to the 4 position, right? I define P, the 0 component of the 4 momentum to be this. And with that definition, it turns out that one can show that that component is the energy. So I'm developing everything mathematically over here. So I don't want to make any claims that, oh, the 0 component is energy yet, right? I define it like that, and then later I'll show that it's equals to energy. So that's how I try to take most of the physics. Yeah, I mean, when you graduate already, you have a lot of time, you can slowly think about things like that, right? In the competition, you just remember and just apply, right? So yeah, so I'm trying to share with you all the luxuries that I've had, slowly deriving all this in my own time. Okay, so this is the 4 momentum, right? It's just m times the 4 velocity, and you see that the m is here, it's a rest mass. There's no 4 mass, right? It's just rest mass. So actually, there's almost, it's a bit misleading to think of it as a Lorentz, as a like when you say your mass increase or you boost, it's a bit misleading because from the mathematics point of view, there's pretty much only one mass that we define, right? I prefer to think of it as just the rest mass. Yeah, I prefer not to think of it as a Lorentz boosted mass. Okay, so going back to it, Hamiltonian mechanics tells us this is the definition of Hamiltonian, Hamiltonian, yeah, which gives me the energy. If I work it out, I get this. So it turns out, oh, it's very nice. 4 momentum, 0 component is energy over C. Okay, so that's convenient. So we have just derived Lorentz dynamics. Okay, how about electromagnetism, right? How do we derive electromagnetism? So turns out derivatives, they transform. If I transform the coordinates, space-time coordinates using Lorentz boost, the derivatives actually correspond to inverse of the Lorentz boost. Yeah,
Especially sometimes between the difference of covariance and
yes, I'm glad somebody brought it up. So this is what we say by the position, right? 4 vectors are vectors, they are contravariant vectors, right? And then the derivatives, they are covariant vectors, they transform under inverses. So yes, very good, right? So this actually goes into the study of this covariant and contravariant vectors goes into general relativity, which is a very fun topic. So yeah, you guys should spend some time studying it after your exam, after your competition. So yeah, so why do I want to define derivatives? Because later when I talk about fields, I need to talk about derivatives of fields in order to define the dynamics. So electromagnetism, just now we define an action, right? Turns out that's the only action we can do because we only have proper time to work with. So what if I want more mathematical structure, right? Previously the only Lorentz invariant scalar is the proper time. But now I want to construct more invariant quantities under Lorentz transformations. So it turns out that we need stuff that transform non-trivially under Lorentz transformations. So basically, we define a 4-vector field to be something transformed like that. Wait, it's a bit okay. I'll basically like to draw a picture again. So imagine that I've just normal space in it. Okay, so let's say this is the origin. And if let's say at this point, I have a field that assumes what's a scalar field? It associates every point in space a single number, right? So for example, electric potential, you can say that phi, the electric potential of this point is I don't know, 0.5, and here is like 0.1, right? Then what if I rotate this space? Right? That will just correspond to moving this 0.5 here and moving this 0.1 here. So now the new field has equation 63. Right? You basically rotated the value such that this number here attached to this point in space is now brought to this point in space. You suck it up, put it here. Okay? But what if I have vector fields? If I have vector fields, then with every point in space, you have a. Can somebody complete my sentence? Vector, yes. If you have a vector field, then okay, I don't have to use but a vector field, then every point in space, you have a vector, right? Maybe this guy is here. What's the example? Vector field is electric field, right? Okay, so this vector with the components, right? The components are 1, 1, 1, and oh wait, this is 2D. 1 and 1, and this one perhaps is minus 1 and 1, let's say, right? Then if I rotate the vector field, there's actually two so-called two ways you can rotate it. One is I say this guy, I bring it here, right? The component doesn't change. It still remains 1, 1, right? So even though I rotated the point in space which is attached to, right? I didn't rotate the vector along with it, right? But I could have alternatively said that when I rotate the field, right, I also want to rotate the components of the vector. And instead of having this, right? I'll rotate the vector along with it as well. In fact, you can do even crazier stuff. Nobody said that you have to rotate it along the same angle. You can say that I rotate it along the minus angle, the minus of the angle. So I can say I attach this guy gets rotated here under the inverse Lorentz transformation. So roughly speaking, that's the equation for rotating vector fields. When your space-time gets rotated, right? Fields that you associated with each point in space, structures that you plug at each point in space. If you rotate the space, you can say that, oh, I want to rotate the structures as well. And these are known as, if you study math, this is known as representations of the group. Right? In this case, we are considering the vector representation of the Lorentz group, which is a spin 1 field. So what's nice about that? Okay, so if I have 4 vectors, right, it turns out I can form an invariant dot product, right? If I have 2 vectors and I consider their dot product, if I have 2 vectors, I consider a dot product, and I rotate with a normal spatial rotation, the dot product remains the same, right? So likewise, I can define a dot product in Minkowski force spacetime, and this dot product is invariant under Lorentz transformations. So this is how we define Lorentz scalars in physics. So now with a whole new batch of Lorentz scalars, I can form many new actions, and this is where the fun begins, right? So for example, if I want electromagnetism, I take the vector field I created just now, and I couple it with I contract it with the position of the particle. If I do all the machinery here, I get the Lorentz force, right? Maxwell equations is a action which involves the vector fields. Right, it's actually a gauge theory, right? And then you can even do crazy actions. So these two are physically relevant because in real life you have equations 66 and 67. But the fun part about theoretical physics is that you can create universes of your own where you have exotic actions, right? All these funny actions. This turns out to be relevant in some hypothetical theory of action and electrodynamics, and most of theoretical physics studying these, right? So yeah, so how about spinors? Turns out that Lorentz group, the Lorentz transformations, representations of the Lorentz transformation doesn't just stop at electromagnetism. You can actually have you can change the spinors as well. So if you've heard of the term that, okay, so this is how your four vector transforms under Lorentz transformations, right? Then I can define a mathematical structure. Instead of having a 4 vector, I define a vector now to be 2 complex components, right? Complex numbers. Then now, how I can say that under Lorentz transformation, same the rapidity like that is W, right? Then I say the spinor transform under the Lorentz transformation in this way. So how is that nice? And let's say this is how it transforms under Lorentz groups, this is how it transforms under rotations. You can see that if theta, right? If I want to go back to the original spinor, I need an angle of 4 pi, right? Because 4 pi over 2 is 2 pi. Wait, this is I can define the spinor to transform under this way. It's a valid mathematical structure. It's a valid representation of the Lorentz group or the rotation group. So it's okay if it's a bit too much, but this is what they mean by the spinor. With electron, you rotate 1 round, you get a minus sign, right? Because it divides by 2. So these are valid. You basically get, when you consider math of group theory, you get spin, and that's cool to me. Yeah. So yeah. So okay. So that's not all, right? Turns out you can define. There's a lot of representations, infinitely many. In fact, you can spin as many as you want. So scalar field is here. This is neutrinos. Right? Neutrinos is a type of representation under Lorentz group as well. So by considering the Lorentz group and representations of it, you get pretty much all the particles you get in the standard model, right? And this is neutrino. This is electromagnetism. This is, I'm not sure. Yeah. So if you go to spin 2, all the spins arise from it, gravitons, everything, they're all constructed from representation of the Lorentz group. So okay, so I didn't have a lot of time to fill in these slides, but what's the idea of general relativity is that space-time is not just Minkowski, it's not just R4, it's not just 4 real numbers. The idea of general relativity is that I want to generalize the notion of space-time to say that every small part of it looks like R4, but then I can glue many parts of it together. So if you heard of the manifold theory, like for example, they say the donut is a manifold, the sphere is a manifold, right? And there are different type of manifolds. So the idea is that locally, right, if I'm at this point in the manifold, the surroundings around me look like Minkowski space-time. But if I take the bird's eye view, it's not Minkowski space-time. And black hole metric. So far, right, what is the Minkowski metric? It tells you how to measure distances, right? So it turns out you can in general relativity, you always solve for the metric. And when you solve for the metric, right, basically after you solve for the metric, you're done with the entire theory, right? Pangkang lo, right? Okay, sorry, maybe you guys don't understand NS lingo. But when you're done solving the metric, right, you're done with the theory. You have solved everything you need to know about theory. So what does the metric do? The metric, sorry? Yeah, correct. So from the metric, example of one metric is this. So this is basically Minkowski, the metric that we saw just now, right? The space-time interval is a way to measure distance. This is the way to measure distance for a black hole, near a black hole, right? Yeah, so this is the way to measure distance near a black hole. And from the notion of distance, you can measure curvature and every single thing from it. So if you want to see, you guys know black hole horizon, right? When you pass the black hole horizon, you're doomed, you're bound to fall into the singularity. So it turns out that if you consider this as a way to measure distance, the boundary at which the black hole transitions, the event horizon is given by the point where this thing is 0. When this thing is 0, right, the dr and the dt flip component, and basically time becomes space and space becomes time. And every geodesic from there, you're falling into the black hole already. Yeah. Okay, but anyway, I hope to pick your interest in theoretical physics. So actually, the reason why I want to give this talk is because I studied representation of Lorentz group and I was very intrigued by it. And I was like, you guys are the top in physics for your age, right? In Singapore and pretty much in the world, right? But I realized that a lot of physics Olympiad people, they don't end up going to theoretical physics. So I hope that This was a sales pitch. Yeah. Okay, but another point, more importantly, I would like to encourage you guys, don't be too stressed about it. There's the greatest waste of talent, in my opinion, is when Olympiad people, not just physics in general, when Olympiad people, they are too focused on the Olympiad, they study too hard, they get too stressed out, they get burnt out. I burnt out for computing Olympiad. And so I don't want you guys to burn out because you guys are the bright minds, right? And it'll be wasted if you burn out all your energy on this Olympiad when there's a lot more of theoretical physics to explore. And in fact, most of the best theoretical physics people, they didn't even study physics in uni, right? The best guy, he actually studied history. So point is, you got a long road ahead, right? Slowly, enjoy the process. And yeah, I hope that my sales pitch was convincing. Okay, thank you.
Thank you so much.